Hi, welcome to office hours, virtual office hours that is. This is going to be a regular feature in which we try to answer questions you've posted to the forum, questions we think are important for future work. First question of the day, why is the magnitude of the derivative of a rotating unit vector equal to theta dot? Excellent question. We're going to go into this in some detail in just a moment because we're going to make great use in this course of what are called body coordinate systems. There are many problems in which the position, velocity, or acceleration of a particle is most conveniently described in terms of a coordinate system that is attached to the body, a so-called body coordinate system. And if you do that, you have to take into account the fact that the unit vector is moving. So watch this. In our use of polar coordinates, we encountered the need to evaluate the time derivative of a rotating unit vector. In this discussion, let's refer to the unit vectors as I hat and j hat, respectively. We know that the unit vectors are rotating with an angular velocity theta dot, and therefore have time derivatives di hat dt and dj hat dt, respectively. How do we evaluate these derivatives? In a time interval delta t, the unit vectors go through an angular displacement delta theta, and their tips go through a linear displacement di hat and dj hat, respectively. The magnitudes of these displacements are the product of the unit vector's length and delta theta. Since the unit vector's length is unity, the magnitudes are simply delta theta. In the limit, as delta t goes to 0, delta theta over delta t becomes the instantaneous angular velocity theta dot. Di hat dt is in the direction of j hat, while dj hat dt is in the direction of minus I hat. This gives us the expressions needed to evaluate the time derivative of the unit vectors. Okay, well, there you have it. And in the future, if you can't remember the derivation, just remember the result. The derivative of I hat is equal to theta dot j hat, and the derivative of j hat is equal to minus theta dot I hat. All right, so the next question concerns the video on planar motion, in which it was stated that angular displacement, angular velocity, and angular acceleration can be expressed as a vector. And the question was, how does that really work? And are we really going to use that? Answer, you bet. Vectors are a tremendously useful piece of analytical machinery that enables us to make calculations very quickly with standard operations and keep all the accounting straight. So watch this. Rotation is a very common motion. When a rigid body rotates about an axis, all points on the rigid body follow circular paths about the center of rotation, which, by the way, need not lie inside the rigid body. All lines in the rigid body rotate through the same angle in a given time interval. That is to say, the entire rigid body has a single angular velocity omega. Angular velocity is represented by a vector. The vector's magnitude is the time rate of change of the angle with units of radians per second. The vector's direction is parallel to the axis of rotation. So in a fixed coordinate system with unit vectors along the x, y, and z axes respectively, a rigid body rotating about the z-axis has its angular velocity vector written as omega equals omega k. For example, assume we were interested in the linear velocity of a point on the rotating body. When omega and r are perpendicular, the cross product is especially easy to evaluate. The linear velocity has a magnitude of omega r and a direction perpendicular to both omega and r. Okay, so there you have it. So keep those questions coming. We'll see you next time.